All right, just getting everything straight. All right, so welcome again. Thank you for joining us. My name is Kathleen. I am reaching out to you tonight from Daytona Beach, Florida, and I hope that you are all having a great day and are super excited to be here to learn about computer fundamentals, the very first step in your journey. And some of you will be familiar with what we're talking about, especially if you're already in a technical type of career, or you just are a technophile and you shop for gadgets and whatnot often. But if you're not familiar with the terminology, we're going to go through everything. What we're going to talk about throughout the evening is, it's evening here, so it's good morning, good afternoon if you're in a different time zone. We're gonna just do an introduction to computer fundamentals. We're gonna do that through the game Kahoot. We're gonna talk about what a computer is, what are terms, components, all sorts of things related to computers. We're going to talk about how computers work, and we're going to start off talking about operating systems and their function within the computer. All right. First test of using Pear Deck. Can you guys see the question on the screen? Can you guys answer that quickly and let me know? Let me know if you guys were able to finish the pre-class material, and I think there's different options there for you to pick. All right. Not everybody answered, but we've got a handful of people that did finish and a handful of people that did not finish. So shout out to me, enter into Slack if you get stuck or need any assistance. Let's see. Just checking on Slack. Got Zoom code. Keep asking your questions in Slack. We've got mentors on the channel that can help answer your questions, things like that. All right. So next question. How long did it take you to finish it? That was the pre-class work. All right. So some couldn't finish. Took some of you up to 3 hours. And one person, it took more than 7 hours. That's a lot of work. Thank you for completing that in preparation of our class today. First thing I want to, I guess, throw out there is that the graphic on the screen is very apt when you're dealing with technology. I even see a question in Slack, somebody saying, what does the CPU even stand for? And that is so common in technology. You have a lot of acronyms that if you work in one discipline in technology, even in IT department, if you're focused on running backups, server backups, and somebody else is supporting an application, those two groups do not necessarily use the same language. And they may have acronyms that are the same, that mean two completely different things, depending on what their area of focus is. So the point of this is, don't be afraid to ask questions. That is true in this class, and it is true as you move forward throughout your professional experience. The more questions you ask, the more knowledge you gain, and knowledge is power. And I truly believe that everything you learn, you grow and grow, and so never stop learning. Okay, so what is a computer? Basically, computers are everywhere, but it's not just desktops and laptops anymore, which were the conventional thing you thought of when somebody said a computer. Now we have tablets, cell phones, we have watches, and so much more that perform functions that we consider typical computer functions. So tell me, you can actually enter it in Slack, what are some common features of computer devices? So when you think about computers and then the non-typical computers I just mentioned, what are some of the common features of those devices? Reminding, yes. If you're me, you need all the help you can get with reminders. Input, output, display, yes. Process, certainly. That's huge. Store, that's also huge. These are great, great ideas. And then you could get more specific. You can say they, keep your calendar. They help you write a letter, that sort of thing. Now, can you guys think, weather, can you guys think of outside the box in terms of when thinking about a computer? What are some examples that are not in the traditional sense a computer, but do what computers do, in that they take inputs, they process that input, and they provide an output. They automatically provide an output based on that input and calculation. Calculator, coding, microwave. Our brain is exactly right. The new AC system, a lot of those thermostats, controllers, display. All right. So in our work through the class, the definition of a computer is this. Computer is a device that accepts data or input and processes it in some way to automatically produce a result. And I know somebody said calculator out there, and I think, in the beginning, calculators were really common computer, adding machines, that sort of thing. But now think about computers and what they have to process, video editing, calculations for, launching a rocket, landing a rocket. So, we've gone from calculators to amazing feats. All right. So we kind of just did this through Slack. Let me move you through some of these other slides. So what is a computer? This obviously is the traditional image that comes to mind. Then we have our gaming systems, absolutely computers. We talked about watches. Smoke detector. Is a smoke detector a computer? I would agree, yes, because the input is smoke. It automatically calculates that air quality, I guess, and provides an output, automatically provides an output, which is the alarm, the sound. So the smoke detector is performing the same concepts as a computer, although it's not in a traditional sense. Now this one is an adding machine from way back when, even before me. And it takes inputs from a person and then calculates a result and automatically provides that result to the person that's interacting with the adding machine. So in this case, it is a computer, But note that there's nothing digital about it. There's nothing electronic about it. So going back to that very basic definition of takes inputs and then it calculates and processes those inputs and automatically provides a result, does not have to be digital. And somebody said the brain, and yes, the brain is a computer in that same sense. This is a wider shot of that adding machine. So back to our definition, what is a computer? Burn that into our brain, burn that into our mental computer, a device that accepts data or input and stores it somewhere, then processes the data in some way to automatically produce a result or output. All right, how computers work. Let's go shopping. We're going to talk about some of the components of computers. I have brought up some Apple laptops, MacBooks, and I want to talk about the concepts that are common with computer components when you're shopping. And we can compare the differences at the same time and how the different components yield a different result in terms of power, size. So initially, some of the terms that you see in terms of shopping for a computer, especially if it's an integrated screen, which laptops do, and then other Mac computer, other Apple computers do, you have differences in screen size, and so you're going to see that illustrated in inches. You also see that same thing with iPads. You see the screen size kind of advertised right off the bat. So MacBook 13-inch, 14-inch, 16-inch. Obviously, as you increase screen size, you're also increasing cost. The technology necessary to render a larger screen, there's more components there, so your cost goes up. You will see that different computer companies, they have different types of technologies, comprising their features. Like this is called a Retina display through Apple. This one here, you can see this one is a plain old Retina display, and then we have something called a liquid Retina XDR display. Again, as you add more technical capabilities, your computer gets more complex, you're going to see additional costs with that. Here's an important line item in terms of these computers, and it's relevant to what we're discussing today, and it is the processor, the chip that is included in the device. And so Apple has an M1 chip, and you can see the next gauge has a Pro chip or a Max chip, so different types of chips. And ultimately, what that is telling us is the capability of the processors. So the CPU, the central processing unit, or the brain of these different laptops, you can see 8-core, 10-core. When you see core, that essentially is telling you that that is the number of processors for that chip. GPU, you can see here again, different number of cores. The more cores, the more speed and efficiency you're going to get with your processing. All right. Let's talk about storage. Storage, obviously, this is the permanent storage that they're talking about here. And a lot of times with programming today, applications can get really big depending on what the application does, or if you have a database even that you're storing on your computer. So the more space, the better. And you can see that this storage is measured in terabytes. That's what that TB stands for. And then this guy here, this is our temporary memory. And that is the storage area where when we're calculating using our CPU and our GPU, that's how much space we have kind of needed on hand to process all the calculations that are being performed by the computer. So the more temporary memory you have, that's going to increase your processing speed. The more cores you have, that's going to increase your processing speed. And then one thing we didn't touch on with this permanent storage, but the type of storage technology that you're using is also going to improve your processing speed. All right, let's take a look. Here's a little better breakdown of what those chips store. And you can see that for the M1 Pro chip, it's a 10-core processor with 8 performance cores and 2 efficiency cores. So that's how they kind of break up their instructions. And some cores perform some instructions, and then other cores are designed to perform other instructions. Yeah. All right. So I think we kind of touched on all the concepts. Obviously, if you're in the market for a laptop, we just did some of the work for you. Okay, how computers work. Basic building blocks of a computer: chips and transistors. And essentially, on the screen there, you can see we've got semiconductors. They are very, very small. And so computers consist of tiny components. We call them chips. You may, if you watch the news, you may hear that we're having a shortage of the technology that computers are built from, chips. Chips can contain billions of transistors. So a chip can be just an inch large, and it can have billions of conductors on there. So that is very, very tiny. So the transistor regulates current or voltage flow and acts as essentially a switch or a gate for electric signals. There's a picture of a CPU, so the brain of the computer, the chip. And this particular chip, it runs at a speed of 4.6 gigahertz. And essentially what that means is it's 4.6 billion cycles per second. Super, super fast. On top of the chip is what we call a heat sink. And we talked about the processors being a gate for electricity. So with all that electricity, it generates a lot of heat. We don't want our CPUs to burn out. So they come with a large heat sink, just a metal unit that gets glued to them. And that is pulling the heat off of the CPU. And the heat sinks look like they have little fins. And so that's to distribute air through that heat sink so that it can cool off that heat sink, and thus the heat sink can then pull more heat off of the CPU. CPUs are made of silica, and essentially silica is derived from sand. Let's take a look at the progression of CPU technology. You can see that in 1972, the CPU, the hot CPU, was Intel 8008, and the number of transistors on that CPU, 3,500. So today, well, in 2012. In 2012, they introduced the quad core, so 4 cores, 4 processors, plus a GPU, that graphical processing unit, and that chip had that many transistors. So 1.4 billion. Computers utilize random access memory. It is temporary. So once you yank the power from your computer, everything stored in random access memory is gone, not permanent. It is fast, but it is expensive. It is getting cheaper and cheaper considerably from when it first, from when computer hardware first started being sold. But it can be pricey. And I'm reminded right now that we have breaks, and I didn't talk about this at the beginning, and I apologize. With each class, you're going to have 2 breaks, and the times for breaks tonight we're going to be 7:45 Eastern and 8:45 Eastern. So we'll take that break. Breaks are going to be 15 minutes. So take the time, get up, move around, stretch, move your head side to side, roll your eyes, that sort of thing. And then once we come back from break, 15 minutes later, we'll just jump right into the next topic. Back to RAM. Short-term memory storage is frequently used by programs and instructions to speed up processes, because when you go and access information from memory, say a hard disk, that takes a while. It takes a while to go out, find the hard disk, find the memory component, the data on the drive, and then retrieve that back to the processor. So that's why we have this random access memory, because it's much more efficient for the processor to go out and kind of dip into what's kind of sitting out there temporarily. It's close by, it's easier to access. So it allows the computer to process faster, as opposed to having to go out and search a disk and find the memory allocation and bring it back. This is another type of memory, per se. It's a hard drive. And this is where we start getting into the nuances of when you're shopping for a computer. This is the old version of your storage drive. This is the hard drive, the HDD. It is a platter with heads. The platter rotates. It is slow. It has moving parts. It's less expensive, but it is vulnerable. The biggest thing with these hard drives is if you jostle them while the head was writing to the disk, or you dropped the laptop, it was curtains for your hard drive. When we get back from the break, we're going to dive into the current storage technology, which is single state drive. And I will leave you with this image. On the left is our hard drive. Middle is solid state. Then on the right is another type of storage technology that we'll dive into when we come back. So 15 minutes, come back at 8 p.m. Eastern. I will see you soon. Hope you had a great break, and you are rested and ready to get back on topic. We left off talking about hard drives. And now we're going to get into talking about newer technology, something now that are commonly sold in newer computers these days. So we've got a hard disk drive on the left here. We've got a solid state drive on the middle. And then we have this NVMe storage device on the right-hand side. All are different, and all are used in different ways for different applications. Okay, so performance of each of the different drives. You can see down here in red that don't know that you guys can see my screen. Okay, so over here on the right in red, it says that solid state drives are 5 times faster than hard disk drives. And then that other technology that we saw, NVMe, that is also referred to as M.2, that's actually 5 times faster than a solid state drive. So when you work it out, M2 is actually 25 times faster than HDD. You really don't see new computers being sold these days with hard disk drives. Everything has moved to solid state drives. Now, the difference between the NVMe versus RAM, let's talk about that in terms of storage. So between a solid state drive and NVMe, solid state drives store data by using integrated circuits, while NVMe is actually an interface used to access stored data at a high speed. So the NVMe is actually more advanced than SSD and hence is faster and better encrypted than the latter. When we look at the effectiveness of RAM versus these other drives, you can see that in terms of performance versus solid state drive or HDD, even the NVMe, RAM disk space, the processor can retrieve data from RAM so much faster than it's able to retrieve data from a solid state drive or a hard disk drive. The graphical processing unit is essentially designed to process visual graphical data quickly. And so the difference between the central processing unit and this GPU is that the CPU is designed to handle a wide range of tasks quickly. Though that speed that it actually handles those tasks, that is referred to as clock speed. And the CPU is limited by the number of tasks that can be running concurrently. Whereas GPU is actually designed to quickly render high resolution images and video concurrently, but GPU does not understand as many instructions as a CPU. So GPUs are much better with video graphics and concurrent processes, but they don't understand all the instructions that a CPU understands. So you still need both if you are looking for a computer that can process graphics at a high rate. If you just get a CPU, obviously you're not doing very high level things with that CPU. It's very basic processing, not very fast, especially when video and graphics are concerned. Now this is the main board, logic board. You can also hear it referred to as motherboard. Different components to the main board. Obviously, you're going to need a place for your CPU. You can see the CPU is stored in this area that looks like it has a square in the middle. On top of that CPU, that's where your fan and heat sink will go. The heat sink has those fins that kind of pull the heat off of the CPU. The fan is actually blowing on those fins to cool them down even faster. You have slots to put in your memory cards. You have something over on the right here, which is CMOS battery backup. And we talked about with computers and memory that, especially in the case of RAM, if your computer loses electricity, essentially anything in RAM is lost. It's temporary memory. It's only stored there when electricity is hot. But when you turn off your computer and you don't have electricity, even if you don't have battery power, somehow your computer still retains certain settings, even without electricity. And the thing that actually stores all that system level, basic level information is run by this battery backup. Very small battery. It looks like a watch battery. So it's not powering a whole lot. Once the system actually needs to power up and process more complex instructions, the CMOS battery is not gonna hack it. It's actually only there reserved for basic instructions. We have different types of connectors on this board. You can see here it's a 20-pin ATX power connector. So that's where your power is going to plug into the board. And each one of these plugs, you've obviously noticed that you're using a mouse, you're using a keyboard. Each one of these plugs is uniquely, it has a unique form factor. So here it talks about 20-pin. Obviously that plug is going to have 20 pins where you have a USB that essentially does not use pins that are visible, but it is a key, does have a key so that you can only put it in the slot one way. Some older display, mouse input, those types of devices, you can see that down here in the lower portion of the screen, those are those older input connectors there. Now everything is kind of a hot swap USB. You can pull it in and out. It used to be that when you had connections going to these two types of connectors, you had to reboot the machine for it to reactualize that it had that device plugged in. So it wasn't, it didn't recognize that device instantly if you needed to do a full power off, power on to get it to initialize that port was taken. You can see we've got here PCI slot, 5 of those. So that's where you're going to see your storage slotted in. And there's up to 5 slots there for 5 different devices. I'm going to start with an analogy to kind of talk through how the different types of memory versus processor work together. And that analogy has to do with food in the kitchen, right? So you've got, if you consider the hard drive your refrigerator, RAM your workspace for cutting up vegetables, or storing vegetables that you're about to cut up, and then your CPU actually processing those vegetables, so performing the work of cutting them up, moving them onto the CPU, off of the CPU, or in sense, onto the cutting board, off of the cutting board. That's the process that data is managed within the computer system. So your data or your vegetables are stored permanently in the hard drive when you don't readily need them. So when you're not actively needing to chop up and make dinner with that vegetable, everything's stored in the hard drive or the refrigerator. Now, when we're ready to start making dinner, start processing that vegetable, chopping it, then we actually have this temporary storage place between the hard drive and the cutting board, and that's our RAM. So it's much faster for us to go and reach over to the side of the countertop to retrieve a vegetable than it is every time we're chopping a different vegetable, going back to the refrigerator, pulling out that vegetable, bringing it back to the cutting board. And then if you don't need the vegetable, going back to the hard drive, finding a spot to put that vegetable back. So that's kind of also how the computer works with data. So it'll retrieve data from the hard drive, move it into this temporary storage area, and then quickly, as processing is required, process that data by pulling it into the CPU, processing it, and then pushing it back out to that temporary memory. The way we actually provide data to a computer is through input devices. And you can see a few input devices on the screen. Input devices, output devices, those are actually, you can hear them sometimes referred to as peripheral devices or peripherals. And so on the screen here, we have earbuds. We've got a monitor as an output device. We have a mouse as an input device. Go ahead and on the screen, give me some other examples of input or output devices, either one. Keyboard, we don't see keyboard up there, right? USB, that's an interesting answer, because USB is actually the method that we connect to a computer. It can also refer to a storage device, so a USB drive. But USB, we're really retrieving data off of a USB if you're thinking of it in terms of storage. Headset, camera, yes. Keyboard, yes. Webcam, mic, perfect. All good responses, all important things to talk about. Touch screens. Let's see, we'll talk about later gyroscopes. When you're thinking of virtual reality, gyroscopes are input devices. They actually tell the computer about position, maybe of the computer itself. All right, so when we're talking about input and output devices, are the items on the screen, are the two technologies on the screen, would you consider them inputs and output devices or something else? I like this example because it is tricky, right? You, in the technical sense, an input device or an output device, they're hardware. So Cortana and Siri, they're actually software. So you provide inputs and you receive output, but the method that you're providing that input or output from a hardware perspective is through keyboard or microphone. Output is display or speaker. So that, I like that question, because yes, you are interacting with this software, but the actual hardware that you're using to interact with that software are those input and output devices. What about barcodes? Is that an input or output device? This one also provides a better conversation around it, because the technology required to use with a barcode, that's actually going to be your input. So that barcode reader, whether it's one of those funny looking gun type of barcode readers or it's the camera on your phone, that's actually the input device. And then of course the output device, whenever something interacts with a barcode, the output could be written to the screen, it could be written to a server somewhere. It depends on what the barcode is actually coded to do. So we talked about input devices a little bit. Let's talk about virtual reality, augmented reality, mixed reality. All of these things really involve taking input and output, so the hardware device, and mixing different variations of reality, depending on what the programming technology is designed to do. So let's talk about, first, let's just define what virtual, augmented, and mixed reality are. So augmented reality, it is using a real world environment and you may see something virtual laid over. Whereas a virtual environment is completely virtual. There's no reality. And an example of the augmented reality, really big, popular thing that came out recently was the Pokemon Go. It's not too recent, but Pokemon Go, and there are things even now that use that same sort of technology setup where you could see with your camera an actual representation or visual of real life. Say you were looking at a fountain. And with that application that was utilizing augmented reality, if your phone was showing you a picture of a fountain, that augmented reality would overlay a virtual character. So that was augmented reality. Whereas virtual reality, you see that a lot in video games where you're interacting with this environment, but it's completely software. It's all virtual, and none of it is actually a real life. And the input for these types of technologies, of course, you have a computer that you're using, whether it's your phone, or you can see this mask on the left here. It could be a mask setup like that. There is the Nintendo Wii, and that uses a couple of joysticks that you hold in your hand. They utilize gyroscopes. So the input is actually position, and that gyroscope can assess where in position that item is in relation to what it's trying to show you through your display, your virtual display. Now, there's also mixed reality, and that's a combination of virtual and augmented reality. And there's more things coming out technology-wise with that utilize mixed technology. An example is Microsoft's HoloLens. So that's a technology that is mixed reality, considered mixed reality. We also have in hardware communication devices. Obviously, we would be nowhere without network interface cards. We would not even be having this class this way. So wireless adapters, network interface cards, or NIC cards, they're often referred to as these actually are connecting with servers, networks. Your wireless adapter in your home is connecting to a wireless router. Your network interface card connects to your network through a cord, an Ethernet cable. Okay, so that is hardware. So we did our Kahoot, and we went through the concepts for talking about the different components of hardware. At this point, how are you feeling about the subject matter, the hardware topic? Because we're about to jump into software, and I want to make sure that you guys are feeling good about your journey so far. So we've got, most of you guys are feeling good. We've got a couple that may be a little confused. If you are confused, please feel free to reach out to me, your mentors. I can definitely answer questions, anything you need to help flesh out some of the concepts that we're talking about. Sometimes just Googling something, there's explanations out there that are helpful because they also come with pictures and comparisons, things like that. But please reach out to me. We'll definitely answer any questions you have. So operating systems are, it controls basic input output of the system. It manages the hardware, power on. What does the power on button do? What is the effect it has on the system? All the way to where to find music, what to do if you want to open up a music file, it manages coding. When we're coding something, we are coding and working within the operating system. The operating system also knows how to execute that code. So operating system is system software, and it manages computer hardware and software resources and provides common services for computer programs that require different operations to function. One thing that comes to mind with operating systems is you have all these different applications, and every company could create their own program. But in order to get that program to run on a common device, that program needs to understand a set of common instructions in order to interact with that device. So the operating system serves as the library of those instructions that both the hardware and that application, that software needs in order to run. Where you have issues between software and the operating system, those are called bugs, and that can be visible in the sense that if you try to run an application on your device and it doesn't launch properly, obviously there was an issue with how the operating system managed and interpreted the software during launch. You can see at the bottom there, those are different types of operating systems. And the open source operating system that I was referencing is Ubuntu. That is a Linux open source software. But then you also have Linux itself as an OS. It's run on servers. You have, let's see, Windows, Android, iOS, pretty common. And then some others that you maybe don't recognize typically as operating systems. The different operating systems are going to provide a different set of approaches to running programs and interacting with hardware. So that is why you will see, like with phone apps, you'll see this is the iOS version of the app, and this is the Android version of the app, because each operating system on those devices handles instruction differently and provides instruction differently. Essentially, that operating system is managing inputs as they're coming in from hardware. It's managing instructions where to direct that particular data. It is managing how to launch applications, controlling and monitoring system activities, things we don't even think about. Now let's talk about another component of operating systems, and this is kernel. And we saw this during our Kahoot. So operating systems, if you think about computers, computers, of course, we learned in the last topic, hardware, and that's typically, so it says a computer, they're talking about the hardware. But installed on that hardware is the operating system. And we have a concept known as kernel. And then on top of that operating system, we install applications or programs. And that is where the user interacts with the computer. The user's interacting with applications and programs, which are running on the operating system, which is running on the hardware. And you can see that the intermediary between applications and programs and the hardware layer here is that operating system. So it's interpreting instructions between these two tiers. All right, kernel. So the kernel connects applications to the actual processing of data. And it manages all communications between software and hardware components to ensure that it's usable, reliable. And so this kernel layer here, it connects the CPU, memory, disks, any devices, mice, keyboards. And it actually manages how each one of those items interacts with software or those user level applications. The kernel is a computer program and it's the heart and core of the operating system. Since the operating system has control over the system, so the kernel has control over everything in the system. It's the most important part of the operating system. Whenever a system starts, the kernel is the first program that gets loaded after the bootloader, that initial instruction to start the operating system, because the kernel has to handle the rest of the instructions that the system is receiving, sending through the operating system. And the kernel remains in memory until the operating system is shut down. The kernel is responsible for low-level tasks such as disk management, memory management, task management, and it provides an interface between the user and the hardware. And we kind of saw that in our display there. BIOS. What the heck is BIOS? Basic input-output system. So the BIOS includes instructions on how to load basic computer hardware. So it includes a test referred to as a power on self test or post. And that helps verify the computer meets requirements to boot up properly. And if the computer does not pass post, you will hear a combination of beeps indicating that a malfunction took place. So when you start up your computer, if you hear beeps coming from the computer, that is the computer communicating that it either found what it needed or it didn't find what it needed. And each operating system has a different combination of beep codes that tell us that different things are wrong. So before you ever see anything displayed, you will see some sort of response from the computer in terms of sound if the operating system can't launch properly. All right, we are at break time. So instead of going further into this, I am going to ask for you guys to take 15 minutes, stretch your legs, turn your head, roll your eyes, do your chair yoga, whatever you need to, get a drink, and then meet me back here at 9 p.m. Eastern, and we will continue on to the end of class with our operating system subject. So I'll see you in a few. All right, so basic input-output system essentially is what we're referring to when we hear the term BIOS. It's a firmware used to perform hardware initialization during booting. So power on. How does the computer know what to do when we press the power on button? And it provides runtime services for the operating systems and programs. And ultimately, once the operating system launches and gets booted up, then the operating system takes over. But BIOS is kind of that foundational set of instructions that the system needs to kind of initiate and perform basic booting. All right, so here's a question to you, and feel free to write your response in the Pear Deck there. What does the OS manage? I see your note, Jay. You're hearing a male voice. It's not me. You don't have a video playing in a browser or anything like that. Sometimes that can bleed into whatever other things you're doing, even though you don't have the browser open or the page open for that matter. All right, let's see. What are you guys saying? So what does the OS manage? We have running software, interacting hardware, software, managing software, programs, controlling hardware. I love these answers. They are correct. It is. It's a bridge between hardware and all of their software. So some other examples: sending output to the monitor or tracking files or folders in the storage area, controlling peripheral devices such as disk drives or printers, running different programs at the same time and not letting them interfere with each other, checking to see if users are authorized or are not to access certain things, controlling and monitoring system activities. All right. All right, so here are some common operating systems: Windows, Mac OS, Linux, Android for your phone, iOS for your iPhone, iPad. Somebody asked a question about Debian, and is that related to Ubuntu? It's kind of a similar, I guess, collective effort. And I think Ubuntu has been engineered to be more user friendly. And if you install Ubuntu, it looks a lot like your Mac OS interface. I work on Linux and Unix servers, and so loading up the Ubuntu operating system on my computer is it's just another option for me instead of working through Windows and having to go through a shell program, because Windows code is not the same as Mac code, which Mac code is similar to Unix structure or Linux structure even. All right, take out your phones. Let me know what type of operating system your computers, your phones are using. If you have an iPad, what operating system is the iPad using? Check that out real quick for me and show me your response in Pear Deck there. And a lot of iOS, Android 11, Windows 10. Yeah, Windows, iOS. I'm a PC user for work. So many business applications originally were written to run on a Windows operating system, but at home, all I use is my iPad. I do everything on the iPad. I don't need a laptop. Not everything works great on the iPad. Like some web pages don't interact well with Safari, and they work better with a full Windows operating system. But for the most part, they're great. They're great. It's amazing. Technology is amazing. All right. Terminal. So we talked about terminals. We saw that word come up in our Kahoot. And this essentially is a terminal. You can launch a terminal from Windows. Let's see. This is the command prompt is what it's called in Windows. You can see it's similar to these. You've got these two interfaces. You see this one on the left. Here is Ubuntu. And then this one is just a bash shell. It still looks like it's a a Mac or type of interface, but you can see how the Windows interface is a little different. So each one kind of has a different look and feel depending on what operating system you're running the terminal from. And then, of course, I work with Oracle products, eBusiness Suite, Fusion, that sort of thing. And to interact with file system on Oracle's system, I have to use a shell program that it's even different from these. So it's not native to the operating system, but it's a program that is dedicated specifically to just command line interaction. So you're going to see terminals a lot in working with technology. Essentially, the terminal, you type in your inputs, you enter the input or execute the input, and then the terminal returns the output back to you. All right, what the heck is a shell? So shell is the interface to the operating system. And it's the outermost layer of the operating system. So shells incorporate a programming language to control processes and files, as well as to start and control other programs. And the shell manages the interaction between you and the operating system by prompting you to input or prompting you to provide input and then interpreting that input for the operating system and then handling any resulting output from the operating system. So shells provide a way for you to communicate with the operating system. And this communication is carried out either interactively between the keyboard and the monitor and yourself, or it's a sequence of commands that you can write out in a script and execute, maybe schedule those on a scheduling utility so that you don't necessarily have to be there entering into the keyboard and reviewing the output through the screen. All this is happening on a schedule without your needing your interaction. Okay, scheduling. So that brings up scheduling. What the heck is scheduling? So scheduling is the activity of the OS process manager that handles the removal of running processes from the CPU and the selection of other processes on the basis of some strategy, some priority that is coded into the different processes. So if you have two different applications running, there is a priority given to the processes that each of those applications are running, if not a priority, an order of execution. So if you create a command in one application before the other, obviously the processor is going to execute that command first, that you executed first. Or if there's a certain amount of calculation that's involved where things have to come into the CPU, be processed, and then be removed from the CPU, the scheduler takes care of all that movement. So scheduling is a integral component in the part of multi-programming functionality within the operating system. So multi-programming, multi-processing, and multi-threading all relate to how an operating system processes. And we saw this related to a question in Kahoot, and it said, which out of the four options, which one is not the three, integral operating system functions? And these are actually those three that are the integral functions. So let's talk about what these are. First, multi-programming. Multi-programming is a method of running multiple programs over a single processor by sharing the processor time in the environment. So multiple programs, one processor. Multiprocessing is executing multiple processes at the same time on multiple processors. So multi-programming, one processor, multi-processing, multiple processors, and then there's multi-threading. Multi-threading is the process of running multiple threads to execute concurrently, supported by the operating system. So where we have multiple processes running either on one processor or multiple processors, threading is the ability to break down that process then into concurrent, they call them threads, concurrent operations to speed up, to get to the final result of that process. So again, multi-programming, multiple processes using a single core. Multi-processing are multiple processes using multiple cores. And when we talk about those cores, we go way back to when we were talking about hardware. Within a CPU, you can have multiple processing units. Those units are referred to as cores. And then multi-threading is the ability of a program or an operating system process to manage its use by more than one user at a time, and even manage multiple requests by the same user without having to have multiple copies of a program running in the computer. So multi-threading, you can hear it referred to operating system technology. You can also hear it referred to server technology. So CPU technology. But essentially, a practical example of multi-threading is in the application that I work with, Oracle EBS, there is a payroll process. And so the payroll process, you launch payroll process, and then it goes out and it performs all these calculations. And if you run payroll calculations from start to end, I mean, think about all the people that have to be paid, all the different types of calculations, whether it's, how much to charge for benefits or how much their salary is. That takes a long time end to end. So if you separate that process out along multiple threads, and those threads run concurrently, in essence, you take that process and say you separate that out into 4 different threads. It's processing all that data from start to end as it would if it was a single thread. But now it's separating out those calculations among 4 threads to run concurrently. So you essentially, if you set it to run 4 threads, then you cut down your process time by 4. So the number of threads that you can set a process to run is dependent on the capabilities of the processor, though. So in an example with my system, you can only have, say you have 2 CPUs, you can only have like 10 threads, because above that, the processors just can't handle that much concurrent processing at one time. So I hope that example is helpful. It is a bit heady when you start to get into all these ways of processing, but essentially the takeaway is your multi-programming, not very efficient. Your multi-processing, more efficient. And then your multi-threading, most efficient. It cuts down on time. Calculations are being calculated concurrently. All right, so based on everything that I just told you, send me your interpretation between processes and threads. What's the difference? Yeah, I see like threads are part of a process, or a process broken down into multiple components that can be run concurrently. Yeah, threads are dividing one task. If you think about it, if you have to clean out your garage and you're the only person working on cleaning out your garage is that process. But if you were able to copy yourself, the 4 different versions of you, it's essentially you're cleaning out your garage, but there are 3 other copies of you doing the same activity at the same time. So you've cut your effort to clean out your garage, down significantly. All right. Now we're going to get into files. We talked about files earlier in the vernacular. You open a file. I'm going to send you that file. Where's that file located? So files are spaces on your computer where data is stored. Different file types. We have different extensions for different file types. So in the image, you can see that we've got MSG extensions on files. We've got OST, ISO, INIs. These are all extensions you find on files, along with other common extensions like .doc, .xls, different common business solutions. So depending on the application or the technology, that application or technology is configured or programmed to read specific file types, and that's where all these extensions come into play. All right, metadata. Metadata is the data related to the data that you're actually working with, that kind of builds out additional information about the object or the file that you're working with. So in the example, you can see that there's a picture of a cat. And so when you're interacting with the picture of the cat, you're just looking at the cat. But behind the scenes, there are these file attributes that are storing additional information. And that information can be the file name, the author, the person created the file, the date the file was created. We talked about geolocation. A lot of times when you take pictures with your phone, a geocode is embedded into the file. You don't see that, right? But that's there. It's metadata. So here's an example of what you might see in terms of metadata displayed a little differently for a song. So you obviously, with a song, you think of the artist, the album, the year it was created. But then there's also other different administrative data that are important to just managing data, right? Unless you are into data management, some of this stuff may not even cross your field of vision. So here they have examples of who added the song to, we'll say this is a database, when it was added, what was it encoded with? So what type of programming or application encoding, media kind. So that goes to that file extension. So you will see for music, they have MPEG file extensions. This is that type of media. File attributes were a callback when we were in the Kahoot game, and they were asking us about file attributes and what was and what wasn't. And a couple of the options were read-only and hidden. And so if you go in and you look, this is, of course, Windows that I'm reaching out to you on, but here's a file within Windows on my hard drive, and you can see that the file extension is a .doc. If I right click and I go to properties, that is where these file attributes can be seen, and you can turn them on and off and whatnot. So those are file attributes. Of course, on a Mac, you're going to access your attributes a little differently. Depending on any file system, they're engineered, developed to have you interact with the graphical user interface in different ways. Obviously, if you're using a command line, then instead of having these graphical interface components, you are actually going to be writing out commands that, you may in a command say, file XYZ attribute read only true. All right, and that means that you want to turn on the file's read only limitation so that people can't make edits to that file. They can only read the contents of the file. So those are file attributes. All right. Directories and folders. Directories. I just showed you my directory on the PC. And directories are essentially locations where you store your files. Files can be grouped in folders. And when we share URLs, essentially we're pointing you to, on a website, a specific directory and a specific page within that directory that makes up that website. Sometimes when you click on a URL, it launches a specific file that is stored on that page as well. So if you ever go to Google, you click a link and it opens a PDF. Essentially, that link is the directory, the location of that file. You can see in the graphic here, we start with a root directory. And the root directory, at least on PCs, is the C drive. That is commonly what you see. Of course, depending on how you partition your drive, you may have D drive, F drive, etc. Depends on how many partitions you've separated that drive out to. But standard install, your root directory is a C. And this stems from way back when there was an A and a B drive. I won't get into those, but that's why we start with C and not A or B. The directory is a series of folders or files nested to make a structure. This is the file structure or the file system. You see that referred to. All right, so I'm taking the temperature again. Go ahead and click on the face that best describes how you're feeling right now. Okay. So people are good, they understand. We've got a couple of folks that are confused. So I am going to invite the folks that are feeling good and are ready to go to kind of close out this session of the class and go on with their day. But the folks that may be confused, I definitely am here. I'll stay on for as long as you need me to answer questions and talk through some of these concepts that are new or confusing. So let me know if you want to just throw your questions into Slack. That's fine. If you want to just take yourself off mute and we can talk through it, that's good too. But for those of you dropping off, thanks for spending this time with me. I will see you the evening after tomorrow, where we will pick up and start talking about storage concepts. Thank you.
Thanks so much.
Thanks. Have a good night. I'm a light bulb.
Hello, I have a quick question on the multi-threading versus the multi-processing.
Mm-hmm.
Just like a little bit more in depth of like an explanation to defer the two.
Okay. Um, let's see. So the concept of processing is you're taking processes, and a process can be just any type of calculation or reception of instruction. So a process can be open this application. If you've ever been on your computer and you have launched your browser, your email, and you kind of click, 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 and you just click all these things at the same time. Each one of those is a process that the CPU is handling, is interpreting and generating a result. So you can, the different technologies, let me bring up the slide to help. So the difference between the three is multi-programming is kind of the slowest method for managing processes. And that is where you've got multiple processes and one CPU handles all of those. And that's going to be your older technology. Where we get into multi-processing, that is, you often see when you see references with buying computers that there's a multi-processor. So that CPU is actually, or that chip is actually comprised of multiple CPUs. And so those CPUs can actually separate out those processes amongst the different CPUs so that each process kind of gets handled in as they need to concurrently, right? So those are separate processes, so separate instructions.
Right.
But when you get into heavy calculation within a process, that's where multi-threading can really benefit you, because you like I was saying, you have a series of calculations. Like, think of using a spreadsheet, and you the spreadsheet is performing all these calculations. Have you ever used Microsoft Excel?
Yeah, sure.
So the spreadsheet, you're going through and you're making adjustments to values in different cells, and you have all these formulas that are set up in the spreadsheet, right? So every time you make an adjustment in that cell, it has to send out a command to calculate the new values of all those cells with formulas. And so that is where threading can help, because the processor doesn't just take that one process and do it beginning to start. It actually chops them up so that you have like 4 starts and 4 ends of that process. And then the processor can actually net back together. Okay, well, this was one process. I chopped it into 4. I processed all these 4, and now that's finished, and I'm returning the results back to the software, the user, as if they don't see that I chopped this up and made it more efficient. They just see that they gave me this command, I completed it. They don't need to know how I finished it. I don't know if that is an improvement on the explanation, but it's
Yeah,
better
it's a good
handling.
example. Yeah, it's a good
Okay.
example.
It's just more efficient, right?
Sure.
More intelligent.
Is that like the main takeaway I should just know, is that the multi-threading is like just a really efficient way for a computer to do their job?
Yeah. Yeah. And when you are working in terms of coding software or coding something that is being processed by the processor, you definitely want to keep in mind when you code, is that functionality beneficial to what you're developing, right? So would this process benefit from multi-threading support? Is that something that I should keep in mind? Definitely, I gave the example of the payroll program, but any large amounts of calculations. So the newer computers, the heavy computers that are coming out these days that are kind of generating all the calculations for AI and data science and things like that. There's so many calculations and analysis that have to take place that to do that kind of start to finish, the computers are so powerful because they can break that processing down into concurrent events and process all those different events and then kind of net the results back together as if, it's seamless to the user. That I didn't see that you sped this up by a factor of 8 or a factor of 10.
Okay. So multi-threading is something that you have to program. It's not already in the computer.
I think the capability is within the hardware and software. So that capability comes with the components that support multi-threading. And then as the developer, you may have to set up a series of settings. It depends on what you're developing, if that's even an issue, but know that it is out there. So if you are developing something that's incredibly complex and is a heavy strain on system resources, that you do have this technology that you can leverage to kind of improve the performance of whatever you're developing. So it's not necessary. Obviously, if you're dealing with an operating system and you're coding with libraries that operating system understands, chances are your coding library is already going to have that interpretation built in. And yes, if you're not here to listen, I see in Slack people are wondering if we're done. We're done. I'm just answering additional questions.
All right, that helps me a lot. Thank you so much.
I hope so. Let me know, and I can find resources for you that probably will explain it a little differently and may resonate better. Okay, so the kernel manages communications between the software and hardware components. Where you have the shell, that is actually our interface to the kernel, right? So kernel is kind of processing, connecting applications to different components of the operating system, maybe connecting applications to other applications if necessary. Obviously, software and hardware components. So when you click your mouse, how does the system interpret that mouse click? And how is that instruction sent to a piece of software that needs to know that you clicked your mouse? So the kernel is kind of controlling all of those different facets of the computer. Again, it is itself software, right? So operating system is software, applications are software, but the kernel software has specific purpose, all right, to kind of manage the system input, communication, that sort of thing.
Okay.
And one of the things that the description says is that it's the most important part of the operating system. So whenever the system starts, the kernel is the first program or the first software that gets loaded, because when the computer starts, there's a boot, right? It's a very basic set of instructions, says call operating system. And once that operating system is validated and the system understands that the operating system can start, that operating system then launches the kernel software. And that software is kind of all that instruction, library of commands, things like that, that the operating system, in a sense, conceptually understands. So the kernel understands what a mouse click is. The kernel understands where to send a print command, that sort of thing.
Okay, thank you for that clarification.
Is
Appreciate it.
that helpful? Yeah, it's
Yeah, that was much helpful.